Now before I go further into the juicier bits, I want to explain two new containers that I added to the engine that are going to be showing up a lot. So I made my own priority queue, which I called queue array of priority float. It was so in case I made more of these priority queues, their names would all be nicely sorted. The implementation of him is fairly simple. You just have two arrays, one of the priority float object, and then one just the min heap object, and then a priority object. The min heap object of float is just a series of float values that you actually store to create your heap. And priority object is just a corresponding array that will point references or have pointers to your outside objects. So when you actually push something into this, you give your object, which gets tossed into that priority object, and a priority level, which gets tossed into the min heap object float. And then it then uses those two arrays to do the classic sync swim, which are down here, sync swim swap. Nothing too fancy here, it's all fairly straightforward, but having our own implementation of this did make things a lot faster than our previous way of using the std map. Yeah, a lot faster. The default constructor is deleted, we just use a specialized constructor so you can say the size of the queue. And it's +1 just so we can ignore using the first index to make our math a little bit easier. This one is where I got far more original. So I was trying to experiment with ways of storing engine memory in arrays while also putting them in lists cleanly. And along that way, I realized that I didn't really like the way linked lists jump around in memory. So when you have a doubly linked list, you go to the head node. Alright, so you jump to wherever he is in memory, jump to whatever object he's pointing to, jump to whatever the next pointer is, or the next node is, jump to his object, to the next node, jump to his object. And so every time you jump around, you don't know where you're going in memory. You're just jumping all over memory. Who knows? You could be near your next door neighbor, it could be in main memory, it could be somewhere nice in the RAM. Who knows? So what I actually ended up doing was, let's put them all together. Reduce the jumps a lot. So you have your object created right here, and then a pnext and a pprevious stored literally right next to it. So this way, whenever you jump, whenever you're jumping to your next pointer, you get your object for free right there. So you've already cut the number of jumps in half. And you no longer even have to have the data for the p object pointer anymore, because it's stored right next to it. So how do we use this? So you take your pooled resource, and you create a resource pool. Resource pool just creates an array of these guys. And then, because all those pooled resources have next and previous, you can then take those pointers and create a stack with them. So the resource pool is just an array of resources, and then a stack that was created using them. The stack isn't anything too complicated, but first I need to explain the iterator. The iterator is very straightforward. It's just a pointer to your resource. It's a fairly classic iterator, but he needs to be mentioned because all the containers only use iterators. They don't accept the actual object. This is to make the rest of the engine much cleaner because no one actually has to reference the underlying objects. They only use an iterator to pass the containers. So if you want to use this guy, you take your iterator and say acquire resource. And he'll quietly pop one off of his stack and toss it into your iterator. Which, that's just exactly what he does. He moves the stack over and takes your resource and sets it into, or takes your iterator and sets the resource in. So we could do the exact same thing for a doubly linked list. You take your iterator, alright, take the resource, and now use the pointers in that resource as part of the linked list. Also, another hard rule with this is anytime you push a resource, I confirm that the next and previous pointers are null pointer. Because you're using the same pointers for everyone, to avoid any weird contention where two containers try to reference the same data, like the same pointers, I completely separated it. These pooled resource objects can only exist in one container at a time, which for our engine case works perfect. Because say for like a graphics object, it's going to live in the pool until the user needs it, then it's going to go to the active list. Then when the user no longer needs it, it goes back to the pool. It only lives in one of them at a time. It'll just go back and forth. So this was actually a beautiful step, because now in your best case scenario, you actually get perfect caching. Because if you say the first object you want is the first object in the array, and then the second object you want is the second in the array, you get perfect pre-caching because you just walk down the whole length of the array. And worst case scenario, you're just using your next and previous pointers to jump around that same array. So you're still going to get some pre-caching benefits. It's going to be far less in the best case, but this is still worlds better than the just blindly jumping through memory of a doubly linked list. So this is a design we ultimately fell in love with because we found this significantly improved our performance. Where it would normally take, for the same amount of time that it took us to synchronize like 70 double buffers, we could do 250. Easy. So this is going to become a standard that you'll see throughout these videos. It is very, very powerful.